This begins Lecture 2, Electric Potential Energy and the Electric Potential. We're going to talk about electric potential energy, go figure, and electric potential, and then at the end we're also going to talk about capacitance. So if you don't know what that is at all, then you're in the right course. Alright, so 2.1, electric potential energy. So you probably have a pretty good understanding of what each of these words mean. Potential energy, we know from our mechanics course. We would often talk about gravitational potential energy, and it's only natural to expect there to exist some electric version of potential energy as well. So that's what we're going to talk about. So, if you recall, the concepts of work and energy were pretty interrelated. And just as you saw for many problems in mechanics, the energy approach of solving some problems makes solving electricity problems, it turns out, much easier as well. And much of what you already learned about work and energy carries over conceptually to electricity. We just have to kind of draw those concepts back out. So for example, we know that if a force acts on an object through some distance, so you can imagine pushing a box across a garage floor, right? We say that work is done on that box equal to the dot product of the force and the displacement, right? So there's that dot product again. The work is equal to F dot S. I'm going to use S to mean displacement. Displacement. So if it was pushing along the x-axis, that would just be delta x, or x2 minus x1, right? So it goes through some distance, some displacement. And the reason it's a dot product here is because, if you recall, for work, it only matters what component of the force is along the distance direction of motion. In other words, this kind of makes sense. We're trying to find what contribution a force, has to something moving through that displacement. And so if you were pushing down on this box here on the ground, if you're pushing straight down on it, you wouldn't be moving it, right? Unless it's moving through the floor. You'd just be pushing, down on it. Even if that box had some velocity from some other reason, somebody else pushing on it, let's say there's person B over here pushing it this way. So let's say FB, and then this guy here is FA, right? Let's just say these are two people trying to push the box to the right. Well, obviously, person B is doing all of the work, and person A is doing none of the work, right? So the amount that something like the force is in the direction of the displacement. So if the displacement is, let's say, x1, and then it eventually moves to x2 down here, you have this displacement vector here, and FB is completely in line with S, our displacement vector. And so the angle between them would be 0, and the dot product would become just F times S, its full amount. And if you were to talk about FA, person A here, the angle between FA vector and the displacement vector is 90 degrees, right? So dot product is, that would be FS and then cosine the angle between. So cosine of 90 degrees is 0, and so no contribution from person A. So we kind of went over that in the first lecture, this concept of dot product, and it kind of being able to quantify how parallel two vectors are, and it comes into play with work. So moving on from that, the work energy theorem said that the total work done on, say, this box is equal to the change in kinetic energy of the box, right? That's what the work energy theorem said. So that said that the work done from the box moving from point 1 to point 2 is equal to the change in kinetic energy of the box. And kinetic energy was 1/2 mv squared. So 1/2 mv2 squared minus 1/2 mv1 squared, right? And so if you were in my course, hopefully in your course as well, I drew a strong correlation. I would always point these out, where you had work, the total work of something being equal to the difference of some kind of similar terms. It comes into play for lots of different things, and so this is no different. So you have, some quantity here, 1/2 mv squared, and it's just the difference of that quantity at two different points. And so that is something that we would give a name. And so in this case, it's kinetic energy, which we would usually designate with a K, 1/2 mv squared. And so work energy theorem, in other words, says that the total work is equal to K2 minus K1, the difference in kinetic energy at 2 points. And we also learned in our mechanics course, to continue with our brief review of relevant concepts for this lecture, that there can exist some potential energy, gravitational potential energy, say, right? And so you can say that there's the total work that could potentially be done on an object could be accounted for by the difference in potential energy of that object at two different points. So if you have, instead of a box on the floor, if you have a box just kind of hovering on the top here, somebody's holding it, but the ground is down here, right? There's a familiar type scenario, right? And so you have, let me draw this. From the bottom here, if the ground is 0, you have y1 being this distance, and then it would drop down, if allowed to drop. It would drop down to the floor and end up being at y2. We'll just say y2 is all the way down there. So, because the gravitational force is equal to mg, like we covered before, and work is force through a distance, right? And so we are using y to designate this vertical distance here. You have the total work due to this gravitational potential energy situation being equal to the difference in mgy. So mgy1 minus mgy2. There's something really subtle to notice here, and I could gloss over it, but it oftentimes has students scratching their head and feeling like, oh, I thought I understood, but I don't. And so I'm going to point it out explicitly so you don't end up getting caught in that moment. So in this top one, kinetic energy, we have 1/2 mv2 squared minus 1/2 mv1 squared, right? 2 minus 1. The second position here minus the first position. And that's natural because it goes from position 1 to position 2. So y here down here, y, maybe pun intended, is the y subscript's different. Why are we going 1 minus 2 in this potential energy situation? Well, that's because we have designated the ground here to be 0. And we're measuring the position relative to the ground. And so the starting position starts at some distance y1 from the ground, and the ending position is also to the ground, and yet our force is acting downwards, and our displacement is downwards, right? So this is our force due to gravity, and this is also our s vector. And so, therefore, we have this reversal of a situation. So you could equivalently write negative mgy2 minus mgy1. Maybe that makes more sense to your brain. You just kind of got to flip it because we're measuring displacement from the ground, which is not its starting position. Up here, you could say its starting position is where the box starts. Not the case for this one. So that carries over to other potential energy descriptions as well. But anyway, in any case, we have this difference of two very similar things being set equal to the total work from that contribution of things. And so we give those things a name. And so mgy we describe as gravitational potential energy. U, oftentimes I will write it as U sub grav. And that's equal to minus mgy. And there's that minus sign back again to remind us that gravity points downwards, right? And we've designated our origin to be on the ground. So that's where the negative sign comes in. And so finally, the last thing I'll include in this brief review here is that we can have a combination of these things, right? You can have a scenario in which there's some change in kinetic energy as well as some change in potential energy, and oftentimes that's actually the whole point of a thing, right? So if you let this box drop from up top down to the ground, sure, there's some change in potential energy, but just by sheer fact of its movement, it has gained kinetic energy. That's where the potential energy went. If its potential energy is reducing, right, because y2 is smaller displacement than y1, and g isn't changing and its mass isn't changing, then you end up with a lower amount of potential energy as you get closer to the ground. And so it's losing gravitational potential energy. And we know from conservation of energy that it has to go somewhere. It doesn't just get created or destroyed at any point. That's not how the universe works. And so one of the common ways that places that energy goes, or forms that energy takes when it's lost in the form of one, is to get translated into kinetic energy. And so, in other words, what I'm trying to say is you can analyze 2 points, right? We'll call this point point 1 and this point 2, and you can analyze the total energy at point 1 and point 2 and set those equal to each other, right, in an isolated system at least. So we can have the kinetic energy at point 1 plus the potential energy at point 1 set equal to the kinetic energy at point 2 plus the potential energy at point 2, right? All right, so with that fresh in our minds, let's now turn to the electric variant of all these things, right? So the way I want to start this is to not just dive into the deep end. I kind of like to start with familiar situations, but with different kind of quantities and causes of motion and forces. And then we'll kind of slowly wade into the deeper end together. So let's set up an electric field that best matches a gravitational field. That's a natural place to start. So we're going to put 2 parallel charged plates, right? So we're going to have, I'll try my best to do a little color coding here. So we'll have a plate up here, and I'm going to say that that's charged positively, because I remember from that last lecture, that electric fields go from positive to negative. And what I'm trying to do is set up an electric field that's very similar to a gravitational field. The gravitational field is going to be, I'll use green for field for now, straight down, right? If you're on or near the Earth's surface, it's just straight down. That would be the gravitational field. And so we want to do a similar thing, but an electric field. So then down here then, give me some room, we're going to have a negatively charged plate, right? This can exist in real life. Sometimes you have physics instructors putting some impossible situations just for the sake of simplicity. No, this can exist. This isn't that far-fetched. And in fact, we will talk about a situation in which this situation is made into a real-life, very useful component. All right, so given this scenario, the field points from positive to negative, and if you kind of, imagine that this extends off to infinity, right? We'll just, for those very savvy mathematicians in the audience, they would maybe point out that the field wouldn't point only straight down unless they extend to infinity. We'll say it points to infinity. So that means that there's no bending right out here is what I mean. It goes to infinity, and in this portion that we care about, the field points straight down. And so we have this electric field from our positive plate down to our negative plate. And thus we have created an Earth-like universe for our amazing little charged particle that we're going to now incept into this universe. All right, so we have a charged particle. I'm going to make him, well, I'll make him red because he's positively charged. So this is like our box, right? And it is sitting up here at high potential energy, somewhere off the quote-unquote ground. And he is, of course, going to experience a force downwards. It's not going to be m times g, right? Because we're not talking about gravity, but it is going to be something analogous, right? He's going to experience a force equal to Q times E, right? So if this charge is Q and it's positive, right? Q times E. So instead of M times G, Q times E, right? So this is all kind of maybe hopefully jogging your memory from lecture 1 and starting to click here. We have displacement vectors. I'll use white, I guess, or I'll use gray here, because that's usually what I use for axes and origins and stuff. So let's say that y direction, positive y direction, is upwards, and this is y equals 0 down here, yeah? So if we want to describe its journey from up there to maybe down here, right, same particle, I'll just color that in so it's not ambiguous. We'll say that it's going from, what color did I use up here to describe the points? Pink. Let's say it's going from point 1 to point 2. And so therefore, we have y vectors y1 and y2, right? Excellent, excellent, excellent. All right, so what is the work that's done as it goes through this displacement from y1 to y2? Well, it's very, very similar to what we just talked about, right? It's just the only thing different is what the forces do to. It's a force from an electric field on a charged particle instead of a force from a gravitational field on a massive particle. Massive being used kind of lightly because we're talking about tiny particles, but you get it. So the work from point 1 to point 2, we would say, obviously, is equal to F dot S, and the force is pointing down, and the displacement vector would be down. And so the dot product is evaluated as just F times S. And the difference there between the two points, point 1 and point 2, is Q E Y1 minus Q E Y2. So compare this, just for a moment, right? Compare this situation in electrical form to this situation that we just described up here with a box falling down. We identified the same points, same kind of displacement vectors, right? The only thing that's different is the type of field and the type of particle and why it's acting. So we have one that's falling down, a force is acting downwards on it through some displacement, because it has mass and it's in a gravitational field. And then we have this one here, force is directly down through some displacement because it has charge and it's in an electric field, right? So there's no mysteries going on here. We can really build off of previous knowledge and just understand how it transfers over to electrical quantities. So here we are again, therefore, we have two things, right? The difference of two like things, QEY, set equal to the total work on the other side of the equation. So we can give that a name, right? And so we're going to call that, it's potential energy, but it's from electric, right? So electric potential energy. You have to be kind of careful here, or I do, because I liberally use subscripts, and there's such a thing that you hopefully saw as elastic potential energy that I usually write as U sub EL, and that could equally maybe ambiguously apply to electric. So if ever there's a case where I'm describing something elastic, I just go with EL, and electric, ELEC, and if they were both in the same problem, in the same context, I would probably write them fully out to keep my head straight on it. All right, so this must mean that electric potential energy is equal to negative, for the exact same reasons that it was negative up here, Q, E, Y, right? And in textbooks, you might see this Q as Q naught. There's, frequent reference to test charges. The whole concept of that, if that's throwing you off, is just that the charge doesn't really exist. It's just a theoretical particle with unit charge, right? So just 1 coulomb that tells you what would happen if you were to put it in this field, right? But I mean, we're kind of making things up all along here, and just for teaching's sake, right? I'm not actually setting up an electric field. There's no stakes here, so I'm just going to say we actually put that charge there. I'm going to have the audacity to ignore the test charge concept for right now. But that's what it refers to. Don't let it throw you off. All right, so hopefully this is sitting well with you so far, with this electric field pointing down and this electric potential energy. We're now going to put a little divisor here, and we're going to talk about the next natural step, right? So we artificially created a electric field, a situation where there was an electric field that best matched gravity. But that's not really realistic for most electric fields, right? So I did admit that there was a device that does have 2 parallel, oppositely charged plates like this. But it's not always the case, and we have to be able to handle other cases, right? So to talk about electric stuff, but to only talk about it strictly as it behaves like gravity is a little silly. So let's widen our knowledge here. And instead of treating a charge in an electric field that is a uniform electric field pointing straight down, just like gravity does, we're going to find a more general expression for electric potential energy in all cases. And mind you, this isn't actually that different from what we did with gravity. So we don't have to ball up gravity and throw it in the trash. We did the exact same thing, or you may have in your mechanics course if you made it through that section of the book far enough, where you found a general expression for gravitational potential energy. So that applied if you weren't on or near the Earth's surface. If you were perhaps like in a spaceship, or you're a satellite, or maybe you're talking about 2 bodies on a cosmic scale that are gravitationally attracting each other, right? So if you're not on or near the Earth's surface, gravity, the acceleration due to gravity, is not equal to 9.81 meters per second, or most likely not. Maybe there's another very Earth-like planet. But it's not in general equal to 9.81. That's just for if you're on or near the Earth's surface, right? It definitely makes sense if you're just pretty close to the Earth's surface. But if you get out here in cosmic space, or just in general, you got to chuck that 9.81 and use a more general expression that works in general. And maybe you even wondered where 9.81 came from in the first place. So for gravitational potential energy in general, we had U sub grav being equal to negative, for the same reason, capital G, which is the gravitational constant, times the mass of one body times the mass of another body divided by r, the distance between them squared, right? Okay, so that means that if you had some asteroid or something over here, and you had some star over here, and it was, doing all crazy star things, you would be able to find the gravitational potential energy between them by finding their masses and the distance between their bodies, or their center of masses, rather. And so you would have this general form of gravitational potential energy that you're empowered to use in any situation. All right, so we're going to do the exact same thing for electric potential energy. So for electric potential energy, let's say we have 2 oppositely charged point charges. So that would be like Q1, and we'll make Q2 the negative one. Well, I'll go ahead and draw it out. Why not? I have the tools to be able to do this. Might as well. minus, and this is minus q. So we know from Coulomb's law, or the electrostatic force, charge force, right, that the force on each is given by, right, electrostatic force, negative k q1 times q2 divided by r squared. Okay, so I draw a lot of parallels between gravity and electricity, right? But don't jump ahead. There's no aha moment yet between these two things, right? There's a little difference here. Well, it's a big deal difference. The r is squared here, and the r is not squared here. And conceptually, we're talking about a force versus potential energy. So don't connect these two prematurely. Let me go through my narrative here, and then we'll arrive at something. So we know that as these two things are attracted to each other, let me see if I can be consistent with my things. Let's see. I don't really have a strictly displacement. I don't know what color I use for displacement. White. All right, well, we'll make it yellow then. As these things move towards each other, right, you can talk about the work that each does on the other. So if this is Q1 and this is Q2, you'd have to talk about it separately, right? So because of Q2's negative electric field, Q1, this positive charge that exists in that electric field, is motivated to move in this direction, according to the left yellow arrow. And likewise, equal and oppositely, because of Q1's electric field, right, which would be kind of like radially outward, right, Q2, negatively charged, is motivated to move to the left towards Q1. And so this is a force acting through a distance, and so this would be work, right? And so you would have a difference between two potential energy positions, right? From, say, R1 to R2, right? And so in the same way that we developed it up there, we have, an F dot S type situation, right? F dot S, right? And they are going to be along the same axis as each other at the very least. And what we get out of this is the electric potential energy term, which is negative K Q1 Q2 over R, right? Because if this is a force times some displacement is going to be like your R, your distance, right? And so that cancels out that little squared part when you're talking about the difference of two amounts of work. And so the term would be negative K Q1 times Q2 divided by R. All right. So this here is the aha moment. This is obviously exactly the same form as this gravitational potential up above, right? So this is very, very similar form, just a different constant, and we're talking about charge instead of mass. And this makes sense, right? This isn't some necessarily mind-bending thing about the universe. It's just two things producing potentially attractive force on each other due to the fields that they produce by just having the fundamental quantity of either mass or charge. And so they move according to either the gravitational field, if you're talking about for mass, or electric field for charge. So it makes sense that the mathematics would be very similar. It's field mathematics. So that being said, I want to point out one last time the difference between these two expressions here, right? So the difference is, for one, this is a force. This is Coulomb's law, or electrostatic force. And this is electric potential energy, not to be confused, even though they look very similar, and it's very easy to confuse them. but they are very different quantities, right? In fact, I'll use a different color even to underline that, just to keep it in your head. The other thing that's different is for the electrostatic force, you have r squared in the denominator, whereas for electric potential energy, there's no square, right? It's just r. All right, so make sure that you understand the difference of those two things, electric force and electric potential energy. Force is what causes something to accelerate. Should be pretty clear by now. Potential energy is the potential amount of work that can be done on something by exerting a force through some displacement, thus potentially giving it kinetic energy, perhaps, right? So one last thing I'm going to point out before we end this segment is that we could flip this conceptually on its head, and it turns out that this isn't just a useless exercise to confuse you. This actually might make future concepts a little bit easier to digest, and so it's worth it to kind of think about this for a second. If you need to, pause and maybe get a cup of tea or something. But an equal viewpoint of potential energy and work is, instead of considering a particle, right, that starts, let me use a bright color here, that starts up here, quote unquote, falling down to here, right, and thus gaining some other form of energy as it loses potential energy, we could instead think of it conceptually, right? Just if we're trying to think of different ways to define it, and there's no actual scenario happening, there's no actual charge here that's dropping in an electric field, it's just me on my iPad. We could think of it as, well, the particle starts here, and we have to put work into this situation to get the particle up here, like lifting a box up off the floor, right? So instead of letting the box fall and saying, well, how much energy did we get out of that? We could instead flip that around and say, well, how much work does it take, how much energy would it take to lift the box up to that quote-unquote starting position? So that's a completely identical way of looking at it, and that will help a little bit. It might help a little bit going forward for some of our future concepts. All right, so next we will talk about electric potential.